Now, actually, there is just a number. So we've got this idea that the rate of change, so if we have a function y equals some number to the power of x, okay, so this would be 2, 3, 4, whatever you like, okay, we have this idea that the rate of change is proportional to whatever size it is. So the bigger something is, the faster it can grow. Okay, that's the fundamental idea of what an exponential is. Okay, and in fact, if you wanted to write this out as an equation, you would have dy by dx is just some multiple of whatever that is. It's literally the same idea. So the rate of change is some multiple of whatever size it's at. But actually, funnily enough, there is one number, so one number down here, one base, one multiplier each time, which, if you consider the rate of change, it's not just proportional to, it's actually equal to. So in other words, dy by dx, the rate of change, is exactly the same as whatever the population size is. Okay, so the rate of change is exactly the same as whatever the population size is. So the question is, well, what is that base down there? And actually, it's a special number called e. Okay, now if you haven't met e, I'll talk about it just in a little bit. E is a special number. It's between 2 and 3. It's irrational, which means it goes on forever and ever and ever without repeating. And it's equal to about 2.718, and like I say, it carries on forever and ever and ever. So it's somewhere between 2 and 3, okay? So if you consider the equation y equals e to the power of x, where e is this weird number, this special number, then that just so happens that the rate of change, dy by dx, is equal to the same size as the population, so e to the power of x. So in other words, if I differentiate e to the power of x, not 2 to the power of x, not 3 to the power of x, e to the power of x, then that is exactly the same as the population size. So in other words, e to the power of x, okay? So my question is then, well, what on earth is e? What on earth is e? Well, one simple way to understand what e is to look at the idea of interest rate. So in other words, with money, okay? So let's suppose I have a really generous bank account that gives me an interest rate of, interest rate of 100% per annum. So in other words, per year, I get 100% interest, okay? And let's suppose my initial amount that I put in, okay, so my initial amount that I put in is equal to £1. So I choose to put £1 in my bank account and I get 100% interest applied over the year, so 100% per annum, okay? So what I could do is consider, right, as a timeline, if I consider year 0, okay, so this is what I put in at the beginning, so in other words I put £1 in at the beginning, okay, and then I just consider at the end of the year how much money I will have, so after the end of 1 year. Okay, so this is 1 year's timeline. At the start of the year, I put £1 in. I get 100% per year. Now notice that I haven't specified when this interest rate is applied. Okay, so let's just suppose it's applied at the end of the year. Okay, so after 1 year, it's applied. So if I start off with £1, at the end of the year, I'm going to get 100% of whatever I put in. In other words, I'll end up with £2 at the end. Okay, so this would satisfy this. If I get the interest applied at the end of the year, I'd end up with £2, okay? But you notice it doesn't specify anywhere when that interest is actually applied. So it could, for example, be applied every half a year. Okay, so in other words, I still get 100% over the course of a year. It just so happens, okay, so this is year 0, instead I'll start off with £1. This is the end of the year, this is year 1. So instead of the interest being applied over here, it could happen that the interest is applied in the middle of the year. Okay, so here, so in other words, after 6 months, okay, so year 0.5, okay. So I get 50% here, then another 50% here, right? So if I get 50% applied halfway through the year, okay, then I'll end up with £1.50. So I'll get 50% of whatever I started with. Does that make sense? So 50% here. And then if I get another 50% applied at the end of the year, then that will give me £2.25. So in other words, another 50% on top of that. Okay. So really all I've done here, this is just 100% applied over the entire year. Okay. This is just saying, well, okay, let's apply 50% then, 50% after half a year, then the other 50% a year later. So I'm still getting 100%, it's just I'm applying it over more frequent time periods, okay? Then let's go even further. So let's say instead of doing it every half a year, let's do it every quarterly, okay? So every 3 months, okay? So same kind of idea. Here's year 0, here's year 1, okay? But instead of it being applied every half a year or every year. Let's say it's applied every 3 month period. Okay, so in other words, I'll get 25% here, 25% here, 25% applied here, and then the final 25% is applied here. So I'm still getting 100%, it's just being applied over more frequent time periods. Okay, so after 3 months, okay, after 3 months, I'll get 25% applied here, which means I'll end up with £1.25. Okay, and then after another 3 months, so in other words, after 6 months from where I started, okay, I'll end up with, well, 25% on top of £1.25 is £1.56. Okay, and then on year, so every after 9 months, so year 0.75, I get another 25%. So 25% on top of the £1.56 I had here is going to be £1.95. And then the final 25% towards the end of the year will get applied here. So another 25% on top of £1.95 is £2.44. Okay, so all I'm literally doing here is applying the interest rate, the same interest rate, still 100%, but it's just being applied over more frequent time periods, And can you see that as you do it over more frequent time periods, you're getting better money at the end? Okay, fairly obviously. So you get 2, then £2.25, then £2.44 if you're applying it every quarter of a year. Now let's do it, but instead of doing it every quarter of a year, every 3 months, let's do it every single month. In other words, that 100% is being split up into 12 individual time periods. Okay, 12 individual time periods. Now, if you do that and you literally just go through, so you say, okay, you take your 100%, and you divide it into 12 individual parts. So in other words, you're getting 100 over 12% are being applied every single month. Okay, you get £1.08, then £1.17, then £1.27, £1.38, etc., etc., etc. Then at the end, after the year has ended up, you end up with £2.61. Okay, so in other words, you start off with £1. And if you apply the interest, the 100% interest, over 12 individual months, so you break it up into 100 over 12%, then you'll end up with £2.61 at the end. Okay? Now, because I want to keep on doing this, and because I can't be bothered to keep sort of working it out, so every month, say for example now every day or every year, every second or whatever, because I can't be bothered to work it out, I need to think about a formula which is happening here. So one way that I can think about this is I'm basically saying every single sort of time period, I'm basically doing 100 and whatever the increment is. So in this case, it was 100 over 12. So I'm basically saying I'm taking my interest rate, which is 100%, and dividing it into however many periods that I calculate it over. So 100%, 100 over n%, okay? Then how many times am I applying that? Well, I'm doing that n times. So for example, with my 12 months, I was basically saying that my interest rate was, well, whatever I had was 100% plus on whatever my interest rate was, which was 100 over 12, and I'm calculating that n times, okay? So if I just think about this not in terms of percentages, but as a raw fraction now, I'm basically saying I've got 1 plus 1 over n all raised to the power of n. That is how much money I'm going to have at the end of that year, okay? That is how much money I'm going to have at the end of that year. Now, if I do that over more frequent time periods, what I'm basically doing here is I'm saying that n is happening more and more frequently. In other words, I've got more n's, okay? So if I now do it instead of every month, if I do it every week, then that would become 52, n would become 52. If I do it every day, then n would become 365. If I do it every second, then n would get bigger. If I do it every millisecond, then n would get bigger. So basically the idea is, if I do this over more and more frequent time periods, n would approach infinity. And I can work out then how much money I should have at the end of the year just by thinking about what happens to n, or just by changing the n as I stick it in here. So as an example, okay, let me just write down this table here. Okay, so let me just create a table of frequency, in other words, when I'm calculating that interest, and then how much money I have at the end of the year. Okay, so if I do this every year, well, we did that right at the very start. If I did the interest over the course of a year, then I'd end up with £2 at the end. Okay, I'd end up with £2 at the end. If I did it every 6 months, again, we did that. Okay, so we did it every 6 months, so I calculated the interest after 6 months, then the interest again after another 6 months, I end up with £2.25. Okay, so slightly better. If I do it every 3 months, so in other words, every quarterly, I end up with, and again, we did that one again, £2.61. Now, if I did it, £2.44. If I did it every month, okay, so I did it monthly, I would end up with £2.61. Okay, if I did it weekly, so at the end of every single week, there's 52 weeks in a year, okay, then I would do this and I would end up with £2.69. Okay. If I did this every single day, so if I calculated the interest split over daily increments, I would end up with £2.71. Now, if I keep going, and just for the argument's sake, I'm going to actually include some more decimal places just to illustrate what's happening here. If I did it instead of every day, let's say I did it even more frequently. I did it every single hour, okay? I would end up with £2.71.8 in my bank account at the end of the year. Okay, and in fact, if I did it every second, I'm going to stop with this one, I would end up with £2.71.828. Okay, so can you see that what's happening? As I change my interest rate so that I'm calculating it more frequently, just simply by using this formula, okay, it's approaching some very particular number. And in fact, the number which it approaches as I do this more frequently is, and I'm going to round here, 2.7182818828459045235336, and then etc, etc, etc. So it carries on forever and ever and ever. So this is an irrational number. It carries on forever and ever and ever, without repeating, just like pi, okay? And in fact, this is the idea. So if you calculate your interest rate over more and more frequent time periods, in other words, the interest is being calculated continuously, then you get this number here. Now, why is this important? Well, we give this number a very special name. This is the exponential number. It was Leonhard Euler who came up with this, the exponential number, which is the reason why we call it E, okay? And the idea is, if you have a situation where you have continuous growth, in other words, growth that instead of happens every year or every day or every minute or every second, if it's happening continuously, the growth never stops, then you basically say that the equation to describe that is y equals e to the power of x. So when you have continuous growth, most growth follows an exponential pattern. In other words, you're multiplying by the same amount each time. But if that growth is happening continuously, in other words, it never stops growing, then we can say that the model to use that, the model to explain that, is y equals e to the power of x. And in fact, most things in nature follow this idea. Okay, so most things in nature follow exponential growth. Most things in nature grow continuously. So therefore, the equation to model continuous growth will be y equals e to the power of